All right. Hi, everyone. Thank you for coming back today. So today our speaker for the Theory of Computing for Fairness seminar series is Marius Papachristou. He's currently a final year PhD candidate at Cornell University, where he's advised by John Kleinberg, and he will be joining the Department of Information Systems at Arizona State University in fall 2025, so pretty soon. He works a lot on algorithms and networks and like large scale social networks and information systems and kind of like trying to understand their wider societal implications. And today he's going to tell you about his work on resilience networks and like frameworks for resource allocation and simulation. And now it's all you, Mario.
Thank you very much, Zuba, for the great introduction. Thanks for having me here. So now I think it would be a good time to start actually talking about things. So today we're going to talk, as Zuba said before, about resiliency networks, frameworks for resource allocation and simulation. And generally, information networks are everywhere, and they play a very crucial role in shaping the economy, society, our behaviors, preferences, and connections. And here in the slide, they have lots of paradigms of like networks being used to actually model everyday interactions in lots of different domains. And my overarching research question is, how do we actually make these large-scale complex systems and networks more resilient? And generally, this research that I've been doing evolves around three axes. First one has to do with the theory axis, where we develop novel theory and models to measure and reinforce the resilience of networks. That draws lots of tools from economics, network science, supply probability, and things like that. The second one has to do more with the simulation aspect of that and tries to develop scalable algorithms and simulations to develop resilient networks. That pertains to algorithms, optimization, data mining, and machine learning. And finally, I have recently been doing some more kind of empirical work where I study complex behaviors of large language model agents in practice. And that involves more like user studies, experiments, and other things more in the empirical domain. And to give you a little bit an idea of what we're going to talk today, I'm going to give you a very simple example of what does something where like something wants to spread in a network and how we can revert it. So I give you two very recent examples. One is COVID-19 and the recession that followed. And the second one has to do with a recent supply chain crisis that happened because of COVID and other geopolitical events. And generally, you could think of all of these systems as complex systems which experience shocks and they undergo contagion. And this results in this cascading spread of failures through the system. For example, in this example below, we have 4 nodes, and at some point, the node on the bottom left gets infected, or like, for example, it could be a business that defaults to its creditors, and then as a result, you can have this failure actually being transmitted to the nodes this node is connected to. So this has to do with contagion, and generally, in order to make these network systems resilient, the goal is to design some model of the world to explain these cascading failures, and also design algorithms to do target interventions. So the talk outline today would be as follows. First of all, the main focus of the talk is going to be about actually deriving a model and intervention algorithms to do that efficiently in large-scale, complex, and dynamic networks. And we will also evaluate our algorithms by using some geolocation data. Our application is going to be focused more in finance, and we will use this geolocation data to infer financial activity and then to test our interventions for resilience. And then there's the interesting next questions that there are several missing data problems that arise in these types of experiments. And the question here is, how do we address this? And this is going to be talking about some more recent line of work where we use large language models to simulate these complex systems and study the macroscopic behavior of LLM, as well as talk a little bit about what biases we found. And I would also like to say that this talk is made for a broader audience, so it's not going to go very deep into theory. It's more kind of like expose things and kind of motivate the discussion on that. So let me now start with a problem of contagion. And let's start with an example of a bailouts in financial networks. So here we see a financial network where there are three entities. You could think of them as three people. These people get, there is a message in the chat, I think. Okay, so you could think of these networks as networks of three people, for example, where they could be working for a job, they could be having some source of income, so they're having some input as assets, and they owe liabilities to one another. So, for example, person 2 owes $1 to person 1, and person 2 owes $1 more to person 3. And then there's also some external liabilities. For example, node 1 may owe $2 to the external sector, node 3 may owe $3 to the external sector as a tax. And generally here, the objective is to maximize the flow of money and minimize, of course, the number of defaults. And the number of defaults has to do with people who cannot meet all of their liabilities. And let me give you a more detailed version of that. So again, we can have this network evolving over time. And here is the network that I showed in the previous slide. We can assume that this is happening on day 1. And then this is the network on day 2. So if you see that on day 2, person 2 lost a source of income, and they already had $1 of liability that they couldn't meet. And now basically the prior debts that person 2 has were accumulated and they were combined with these future debts. So now person 2 may end up owing $4, which are the debts from the previous day plus this day. And generally, again, there is a planner here. The planner was to do some allocations to maximize the flow of money in the economy and minimize the defaults. And here you could think of it very, very briefly as whom should the government bail out subject to a budget. So, for example, if we were talking about the first day, if the government bails out this person, that means that person 1 now can meet all of their liabilities and will be and it will be okay. And on the next day, the government can choose to bail out the person on the top with some amount of money, and then it may be able to reduce some of these debts of $4 to the other ones. So this is in very high level what we will be doing. And generally, the aim of this work is to devise this scalable method to measure the resilience of networks. This method is also going to support dynamic and heterogeneous environments. We're going to give some theoretical guarantees on our algorithms. And the interesting thing, I think, about this work is that you can apply it in many real-world settings. First has to be with financial networks. You can do viral marketing. You can do ride sharing. For the interest of time, I had some slides before for that, but I have removed them in order to be able to finish on time. So let me get into the related work in that for this paper, which, by the way, is joint work with John Kleinberg and Sid Banerjee from Cornell. And lots of the related work draws from the financial contagion literature, where there have been many, many models of describing this contagious process in static networks. The classic works of Allen and Gale, Eisenberg Noe, Elliott, Golub Jackson, and many, many other quite well-cited papers. And there have been some works also that study this case of static network plus interventions. You could get many examples from finance. There's examples in social networks, the influence maximization problem, and the systemic risk literature also kind of studies this question. However, most of these related works are static. They are not dynamic. And there has been a little bit of work on dynamic networks. and dynamic networks of intervention. However, there are some limitations on these existing dynamic models. First one is that there are no optimality guarantees behind the algorithm device. There are no provably efficient algorithms, so these algorithms may have like a high complexity to compute. There are strong stationarity assumptions on the liabilities. And finally, there's applications that are limited to the finance domain, whereas like actually we propose that as a more general framework. And I said before that there are other applications. There is one financial networks. You could think also of peer-to-peer lending. Then there is social networks where you could want to generalize an influence maximization model. And finally, there's also like a ride sharing problem that you could use this model for, which has to do with vehicle dispatches. However, for the interest of time, we're just going to focus on the financial network today. And this other stuff I would be happy to discuss offline. So now let's go to the financial network. And we will start with the two design goals of the planner. So this is the financial network I showed you a few slides ago. And the planner has basically to account for two main design goals. First one has to do with how is someone's asset split upon default. So whenever someone fails to pay out their debts, how are they going to split it? Actually, this becomes a high-dimensional and hard problem, which is some NP-hard problem. And secondly, we have the following question that if there is given a planner with some budget for resuscitation, how should we allocate this budget? And here, someone would think we can take the more central nodes, you can take it by degree, eigenvector centrality. However, these node centralities are usually not a good proxy for allocations, and there is many works in the influence maximization literature that has shown this kind of discrepancy. So let me get started with the actual model of contagion now. So I want you to think of two nodes, I and J, that are part of a bigger network with many other nodes. And these nodes I and J, there is some liability from I to J at time t. So again, the network is dynamic and it's changing over time. And there is some non-negative amount of liability from I to J at time t. Then I and J can have some external liabilities. You could think of them as some external demand they have to satisfy outside of the network. These are denoted by Bi of t and Bj of t. And subsequently, I and J also have some external supply of cash. You could think of it like some assets. And in the end, we also have the planner's decisions, which have to do with the bailouts, which are some interventions that are applied on the node in order to bring them back from default. And these interventions, of course, are non-negative, and they're subject to a budget that varies with time. So we also have this budget constraint that the sum of all of the allocations should be at most the budget, and the budget, the bailouts are bounded between some values. This is more of a like technical assumption to help us with actually rounding the variables later. So the decision variables here are 2 and t. So there are n agents and there is a finite time horizon t that this dynamic network evolves. And first decision variable is how much its agent is going to clear. So how much of this demand that is given to the agent is going to serve. And the second variable is the bailouts that the agent is going to get. So basically, our optimization is kind of in these two variables, pi and zi, for every agent n and for every time step t. And now let's go and see how the liabilities are getting accumulated, and because there is now some dynamics to this model. And first, let's see how this is going to work. First of all, there are some new liabilities that are arriving instantaneously at time t, whereas these are split into something which is exogenous, something that the node actually owes to the external sector, plus endogenous liabilities. These are liabilities to other nodes within the network. And these are the new liabilities. And then there is also the unmet previous liabilities, and the unmet previous liabilities are the previous total liabilities minus how many liabilities the nodes has managed to serve. So the node can serve like up to a point its liabilities, and then the liabilities are getting carried to the next time step. And you can also generalize the analysis, whereas you get a penalty for every time you're not paying something. So you can also have like some interest rate over that and generalize the model. But generally, let's stick with the simplest possible model. And also there are some behavioral kind of characteristics about the agents. The agents, of course, cannot look into the future. So we assume that the agents are myopic. They're just concerned about their present state. And they're also truthful. So they want to clear as much debt as possible. They don't want to game the system. So they're trying to behave according to trying to serve liabilities. And if we sum these two terms, we get actually the liabilities at time t. So again, I repeat, we have the previous liabilities and the new liabilities that are coming, and we sum them and we get the new liabilities. And generally, the assets and the liabilities are evolving as a Markov chain, whereas we have assumed for technical reasons that BI is positive, the assets are non-negative, and of course the assets are non-negative, and the internal liabilities are also non-negative. So far I've talked to you about how liabilities are getting accumulated, what are the decision variables, and generally how is the model between the agents. And now we're going to go to the interesting question, which is how do the agents actually serve the liabilities? So if I start with a simple example, let's say that we have node I, and node I at equilibrium has some available cash, some available supply, which is $120. And the demands from its neighbors is the first one, J1, asks for 25, the second asks for 50, the third asks for 25. So of course, because I have 120, I can serve all of them because in total I owe 100, and then I can set my clearing payment variable to 100, and I can serve everyone. And this is the case where the node can meet its liabilities in full. This is very easy and straightforward on what's happening. However, what if I had 50 and again I was owing the same amount of money? Someone that could think from the planner's perspective, the first thing that someone can think is how can I allocate them so that I minimize the defaults that are happening in the network? And it's not very hard to see that this is essentially a set cover problem, and it's NP hard. So this design rule is not something good if we wanna solve some large scale algorithm and study this kind of allocations. But there is a very natural actually thing we can do, which is also based on some fairness principle, and it's very straightforward and what the nodes could be doing. And this one is if we ration the assets proportionally. So here again we have the $50, and we owe 25 to the first person, 50 to the second person, and 25 to the third person. So these are 100. The first person is gonna get 25% of that, which is gonna be 12.5. The second one is gonna get 25, and the third one's gonna get 12.5. So here, if we do this proportional rationing, the node will set their clearing payment variable, of course, to the available assets equilibrium, and it's gonna split the payments proportionally. So this is something reasonable. This is something also that can help us develop some more scalable algorithms than trying to find the optimal rationing, and is also very reasonable as a behavioral kind of assumption for the agents. And with all of that now, I want to start setting up the optimization problem. And the optimization problem becomes a Markov decision process, whereas we want to find the best control. For the beginning, we're going to talk about the control being fractional. such that for every round, we maximize the amount of money that flows in the economy. So this is what this double summation means. First one is over the time horizon, second one is during the agents. And we want to maximize this total demand served, basically, subject to agent dynamics and these budget constraints. And this is a Markov decision process. It has two empty variables. It is very high dimensional, even for small and reasonable instances that you could think about. This is quite complex now. So first one is to try to do something naively, which is to try to solve the Hamilton-Jacobi-Bellman equations. And basically, we will be doing Monte Carlo estimation to sample and calculate the value function. However, if we want to naively estimate the value function with Monte Carlo, this is going to cause us a combinatorial explosion because, of course, in any given state at a given sample path, I may have to sample many times to estimate the value function, and this is going to blow up combinatorially. And I'm going to get at least 2 to the t problems where t is my time horizon. So basically, if you have a high time horizon, then there's no luck. Another thing that you can do that I got asked in some talk, it was, can you do value iteration? The answer is no, because this is going to become exponential in the agents. So Monte Carlo estimation becomes exponential in the time horizon. Value iteration is going to become exponential in the agents. And instead, our main technical result on solving this type of problem is to do the following. We basically leverage the fact that this model of contagion can be very elegantly written as a linear program. And then we do a little bit of massaging in the Hamilton-Jacobi-Bellman equations, and we're able to drag this expectation from inside to the outside. And that basically, based on the linearity of the model, I'm not going to go into the proof for the interest of time. However, I will give you the informal theorem of what we achieved, basically, and you can look up in the paper how we actually proved it. And we saw that we can estimate the value function by solving t to the cubed linear programs over t squared sample paths in terms of the time horizon. And of course, in the complexity, we have some log 2 over delta divided by epsilon squared that has to do with the accuracy of the approximation of the value function and the probability of error. And this, you could think of them as coming from the Chernoff bound analysis. So the problem then becomes really easy. And basically, an algorithm is like you sample a sample path, and then you sequentially solve the problem, and you forward at every time you solve it, you forward the solution to the next step, and you do that for your whole time horizon, and you repeat that for many times, and then you can show that you can estimate basically the value function. So this is actually some combinatorial kind of trick we're doing, and we actually get this to work on large-scale networks. And now I'm going to show you some instances from real-world data. So here we can run this in large graphs with thousands of states. So for example, here on the graph, I have the execution times as functions of the number of nodes and the time horizon t. So for example, the first one has 10 to the 4th time horizon and around 10 nodes, and you can solve it in a few seconds. The other ones, they have more nodes and fewer time horizon. But for all of these, if you were doing brute force or value iteration, it would take too long to solve any of these problems. And here we can solve it in seconds, actually. So now we're gonna see more like how this is applied in practice, whereas we're gonna deploy this framework to actually look for a real world problem. And this has to do with assessing bailout policies during the COVID-19 pandemic. And here, the challenge is that we don't have that much data about economic activity to create these financial networks. We have very scarce data. There's also a lot of privacy constraints in this data, and that causes this interesting missing data problem. Towards this point, we thought of what if we use geolocation data? So geolocation data are a proxy for measuring actual human activity. And what if we use this data to create a network of liabilities between businesses and people? So here we infer and study these financial networks from geolocation data that are coming from a SafeGraph, which is a platform that actually aggregates this geolocation data. And basically, what we do, we combine this geolocation data from SafeGraph and the US Census, and we created the financial network that actually depicts the financial activity between census block groups and businesses within cities in the United States. So these are for data that we have for many US cities. And we did a lot of data processing to kind of come up with a reasonable model of a reasonable graph for financial network. And I'm not going to get a lot into that because it takes a long time to explain actually how we did that. And what I want to show you is the results of running the algorithm into this data on the city of Ithaca, which is where Cornell is located, around the period of, I think, April 2020. So here is a graph that shows how much clearing payments are being given by nodes. These are either businesses or census block groups, so aggregates of groups of people. And this is how much bailout, how much intervention we gave. This is the result of the control problem. And this is run over, I think, 5 time periods, and these are averaged over the 5 time periods. So, and there's also, I've plotted some robust least squares line here. And basically, the interesting thing here is that there is some emergence of notions of vulnerability and resilience. So a node is more vulnerable if it clears more amount of liabilities, is more central to making the economy functional. And also there is some notion of resilience that we can now very scalably compute. That has to do with how much intervention the node is getting. If a node is getting a small amount of intervention, it gets a smaller bailout. It's more resilient, so it doesn't need a lot of help. And the next thing that I want to show you is the case whereas this control actually becomes discrete and it's not fractional anymore. And this is a very interesting case. Actually, in many European countries and in Australia, for example, the governments chose during COVID to give some stimulus checks that were of a fixed value to citizens, whether they have been affected by the pandemic or not. And in our framework, this actually amounts to making the control discrete and solving the same problem. Now, and the first thing is that from a first principle, this problem seems NP hard, and indeed it's NP hard. We proved it from a reduction from the set cover, and whenever the time horizon is 1, so the problem is actually static, we can prove that this is monotone. The objective is monotone and submodular, and there we can get 1 minus 1 over E approximation. This is, as you know, the best possible approximation we can get. And in the case that there is a variation in time, so in case we have a variable network, we get an instance-dependent approximation. So the approximation ratio we get is 1 minus beta tilde, where this beta tilde measures, in a sense, the amount of endogenous exposure of nodes in the network, and basically measures what percentage of the node's total liabilities are exposed within the network and not outside of the network. So this is what we have so far. We believe that it can get improved, hopefully at some point. And it's an interesting problem because this kind of all of this framework of allocation can be used a lot in like other influence maximization problems. You can generalize decimal maximization problems. There are lots of similarities between the two, and there is a very interesting kind of like research that someone could be doing by bringing these models that are essentially coming from the financial literature into more social networks and these other types of things. And of course, there is also other applications to operations like ride sharing. So in the paper, we have some experiments for vehicle dispatches in ride sharing and many other things. So far, if I want to give a recap, we have developed a scalable framework for decision making in complex systems. However, the challenge that we stepped onto when we're trying to run experiments is that the network data is very, very limited usually. And for example, there are many interactions when we're doing this kind of like experiment, we're trying to infer financial activity. There were many interactions that we couldn't capture because, of course, there were no data for privacy reasons and for many, many other things. So the first potential solution is to use an agent-based model. So an agent-based model has some well-defined utility function, takes some inputs from some covariates, some features you have, what your neighbors are doing, and basically the agent takes some action that changes its state, and that continues, so on and so forth. However, this economic behavior is very rich, and the question is, can you capture everything with some stylized model of behavior? And here, I want to motivate you into kind of thinking about a new way about agent-based models, which are, of course, very important for a variety of domains. So I mentioned financial networks, recommender systems, another one maybe want to model some supply chain relations or a social network. When social network also you have many missing data problems because sometimes it's very hard to sample the social network and get good data sets. And all of these many new things. Actually, we were discussing about this idea of using language models to do this agent-based modeling. And here I'm going to show you a very simple initial application of using them in social networks, actually. So this is a joint work with Yuan, whereas we were trying to actually develop networks using large language model agents. And basically our question here was, do these networks of LLM-based agents show the same macroscopic complex behavior similar to humans? Of course, in the microscopic, like in the agent level pages, it's hard for us to say whether there is this behavior or not. Most likely with the current language models, it's not there. However, the interesting thing is that if you combine lots of agents, you have some emergence of properties that are correlating with what humans are doing. And especially the interesting thing is that we found that the networks that are generated by these agents, they exhibit homophily, they exhibit radic closure, preferential attachment, community structure, and even small world phenomena. And we did many experiments by actually simulating new networks and also experiments on real world social networks. So today I'm gonna show you more about what happens in the social network case, where we have existing data from social networks and wanna see how these agents behave in the networks that they form. And let me show you now what is the social network formation process. So this is me, this is my Twitter profile, and I'm Marius. I'm following 4 users, 650, 70, and 7. I'm doing computer science and I'm graduating in 2025. And here I have some platform recommendations that are given to me. There is person A that follows these other people. They have the same major as me. They graduate in 2026. There's person B and there's person C also. And there are some recommendations. And basically, if you think of me as an agent, I make a choice of who do I want to connect to. And now we take this process that humans are doing, and basically we replace myself with my profile information with some language model, And this language model bot is tasked with forming links with some candidates that the platform is recommending. And the bot has, of course, access to its own features, its connections, the candidate friends features, and their topology also. So we know basically attributes and neighbor connections. And finally, the LLM can output its choices and the corresponding reasoning behind the choices. So, for example, here the LLM bot chooses to become friends with person A, and it's also going to give you a reason for becoming friends with A, like we have the same major, or we're following the same amount of people, and so on and so forth. And you could think of it as a much more rich modeling concept, whereas instead of having just simple features that we have here, you can have your whole like profile information. You can have like a persona personalized for you essentially. And when LLMs are making these connections, we want to discover what biases they're having. How are they making these connections? What is the main driver behind these connections? And we model that with a discrete choice model. This is something that economists love. And basically what it says is that it models the probability that the node I chooses a node J at round T to be proportional to the exponential of some utility of choosing J, subject to, of course, normalization constant among all of the candidates that this agent has been shown. And sequentially, at every round, a user is presented with 15 randomly sampled recommendations, and we want to see what biases are in their connections. And the utility model we're using is something very kind of familiar from the network science literature. We want to measure, first of all, the effect of preferential attachment, basically the tendency of the node to connect to users that have lots of followers, so famous users really. The second one has to do with the triadic closure, which has to do with the tendency of connecting to users that have lots of common followers with you. So basically, we have a covariate that measures the logarithm of the number of common neighbors. And finally, we want to measure homophily, which is similarity on the attributes between two nodes. So here we measure in how many features they are agreeing, and we measure the tendency of connecting to users with similar interests. And the social network datasets we're using are coming from Facebook. So Facebook, there are these 100 college network Facebook datasets. So we actually ran this experiment on profiles of Facebook users back in the 2010s that were using Facebook for college. And this is a very rich dataset because it has features and many other things, and it's available online, of course, if you want to experiment more. And what we found is that the agents are doing more, they're prioritizing homophily. So we have the largest effect is for homophily. Then they're doing triadic closure, and close to triadic closure is preferential attachment. So this is three networks. This is a network from Caltech, a network for Swarthmore, and a network from University of Chicago. And we found the p-values to be less than 0.001, so statistically significant. And also we found it to be robust to the change of the language model. So if you put, here is GPT-4o, if you put Claude or GPT 3.5 or these other models, you could get a lot of consistency in the way that the decisions were made. So of course, one could say here, of course, they have been trained on this data, so we see actually things from the data. However, what I want to say is that, okay, we can combine these biases that the LLMs have and actually use them as proxies for doing some simulations, because on the macroscopic level, this looked quite reasonable to what humans could be doing. And then we also analyzed the reasoning, the textual reasoning that the LLMs gave for making the connections. And you could see that they agree with what we found by fitting the model. And this leaves a lot of room for these large language models simulations that can have many applications where we need to conduct a very big simulation, and we want to see, for example, we are a company and want to deploy some algorithm, and want to see if this algorithm is actually harming people. What if we could do it on a sandbox environment? Or what if we want to do something where we want to evaluate whether a tool that we have been developing at the company is going to improve worker productivity, for example, and this many other things. So one thing that someone could do in the past, they could bring people in the lab, and you could have them actually use your own thing, and then you could send them back, and that could take a year until you would get some good results, whether the system is working or not. However, you can make this much shorter by running an silico user study, whereas you simulate users with language models, and then you take the outputs and give them to real human participants. And this is what we did in the last bullet here. This is some joint work with some collaborators with Microsoft, and we're currently also seeing how users respond to new algorithms. And of course, I also talked about the network formation capabilities in the previous two slides. And this, I think, is a very interesting line of work that I think is gradually emerging. There are several theory problems that someone can think of. For example, if I want to run a very large scale simulation, what is the best thing to do there? And how can I do it so that I minimize the number of queries, what models I'm going to use, how I'm going to store the states. These are several algorithmic problems that people haven't thought about yet that I think are very interesting. And finally, some food for thought is what about fairness of these models? So for example, I want to say that in the network formation paper, we had cases whereas we were putting models like Claude 3.5 in some network formation task, and it ended up that they were attaching only to highly influential nodes. These were the different experiments on the college datasets that I showed you before, but we had this rich gets all behavior, for example. So this is of course a warning that this should be used with caution. We need to be talking more about generalization, what happens with representing the preferences of a heterogeneous population, because in many cases, like actually the fact that the population is very heterogeneous is going to be the thing that makes or breaks your study or simulation. And with all of that, I want to thank you for paying attention to this talk, and I'm happy to get any questions.
Yeah, thanks so much for the great talk. So we can take a few questions right now. We have a bit of time. But if there is no question, we can also end early. Up to you guys.
So I do have a question. So like I think you mentioned that if you have like sort of like homogeneous users, I think it could possibly sort of like affect like your simulation. But I'm like curious, like in general, do you have like some sort of like what are some of like the challenges you faced sort of like using LLMs for simulations, and also like do you have some
Yeah, that's a great question. So, for example, if you wanted to simulate some, if you want to do some market research or something, usually the thing is that you want to fine-tune models to personalize them, but you don't have enough data from agents to actually make personalized models. And then you can, of course, play with other parameters that affect diversity. So, for example, LLMs have this temperature parameter, which is kind of affecting how random is the output that the language model is giving. However, it's not clear what you should be doing, and I think that's one of the big challenges. So there are many times whereas like the obvious solution is to do a fine-tune your models to personalize them into groups of populations, but you don't have enough data within the same clusters, for example. So this is this is one thing that you could think of. I would say, of course, like different populations may have different behaviors, and then you don't want to see like situations where they are just collapsing to doing the same thing, because this is the kind of like diversity, but also increases temperature, also increases randomness, but randomness may be good for diversity up to a point. So there are several kind of like niche issues, I think, here that you could think of. Does this cover your...
Thank
Okay.
you.
Well, I guess if there is no other question, we can probably end here. So like, thanks again, Marius, for the great talk. And yeah, we'll see everyone next week.